Hi, so this clip's about Newton's third law, which is one of the most misunderstood simple laws of physics, and you need to know all about Newton's third law if you're doing physics A level or physics IB. So hopefully this will clear up any misunderstandings that you may have. So it's a misunderstood law, often. Right, so what is Newton's third law? Well, most people quote Newton's third law as follows. Every action has an equal and opposite reaction. And in some ways, this statement of the law is one of the reasons why there is quite a lot of misunderstanding about it. A more modern and useful way of expressing the law is as follows. If object A exerts a force on object B, then object B exerts an equal and opposite force on object A. So I recommend this one is the best one to use, and indeed A levels and the IB utilise this expression often. So now this suggests then that when you have two bodies interacting, that there are pairs of forces, because if one of the objects exerts a force on the other exerts a force back on the original object. And so we do have therefore what are sometimes known as Newton's third law pairs, and it's quite a useful way to talk about forces. And as the second way of expressing the law shows, a few things have to be true. In fact, there's four things. Firstly, the pair of forces, both forces have to be equal in size. They have to be in opposite directions. Thirdly, they have to be of the same type of force. They have to be the same kind of force. And fourthly, they have to act on different bodies. So those are really important, and I'm going to put a cloud around those, and we'll come back to those when we're trying to see where some of these misunderstandings come from. So let's take an example. Right, the example we'll look at is something just two objects in contact at rest on the ground. A nice simple example. So if I draw the ground here, and let's have a ball or something resting on the ground. Now, so there we go, a tennis ball, football or something on the ground. Let's see if we can find the Newton's third law of pairs. Well, the first force that most people think of in this situation is the weight of the ball. Now that usually is drawn acting from the centre of mass. So I can draw that pointing straight down like that, and I'll call it W, or we know that's mg. And now here's where we start to get into trouble. If we ask most people, right, what is the Newton's third law pair to that force? The instinctive reaction people have is to say, oh well, it is the reaction force, and people will often draw on the force at like this. And the force we often call R or N or whatever. But this is where we have to be careful. That is not the Newton's third law pair. Now, it's a bit confusing because the first expression of the law does say every action has an equal and opposite reaction, and that I think is one origin for this misconception, because it's called the reaction force. It's instinctive to think, yes, well that's the reaction to the weight. And even looking at Newton's third law pairs, at first it works out quite well, because they are equal in size if the ball's at rest. They are in opposite directions, aren't they? The weight is down and the reaction is upwards. But there it starts to go wrong. So the first two are true, but they're not of the same type. The weight is a gravitational force, but the reaction force isn't. What type of force is it? Well, for now we'll just call it a contact force. And of course they're not acting on different bodies. They're both acting on the ball. The weight is the gravitational pull of the Earth on the ball, and the reaction is the push of the Earth on the ball. So only fits 2 out of the 4 criteria. So don't be tempted to say that the, in quotes, reaction force R, or sometimes called the normal reaction and labelled with an N, is that the third law pair to the weight. It's not. So what is the third law pair to the weight? Well, look, it's sometimes easier to think about that if we take the reaction out of the way altogether. So let's redraw the situation. Let's zoom in a little bit. So let's imagine that, or zoom out I should say, let's imagine that there's the Earth, zoomed right out, and there's a ball falling towards the Earth up here. Right, now this is a little bit more interesting because we can now, there is no reaction because they're not in contact. So we know that that's got nothing to do with it, but I can still draw on the weight of the ball. The weight of the ball is still an arrow starting at the centre of the mass of the ball and pointing towards the Earth. So I'm going to call that W as before. But what's the Newton's third law pair? Well, it turns out that the gravitational force acts between two bodies, between two masses. So the Earth is pulling on the ball, but the ball is also pulling the Earth with gravity. So I must actually draw the Newton's third law pair as the gravitational force of the ball acting on the Earth. The ball is pulling the Earth upwards as the Earth is pulling the ball downwards. And the only real way to label that is to call it the gravitational force or gravitational pull of the ball on the Earth. So that's why I've drawn it acting from the centre of the mass of the Earth. So now, yes, now this time they're equal, although that's maybe quite hard to believe. I'll come back to that. And they are in opposite directions, that's clear. They're both gravitational forces, and crucially, they act on different bodies. So I can actually this time tick all four ticks. One's acting on the ball and one's acting on the Earth. So this time it looks a little bit more promising. But equal in size doesn't feel intuitively right, does it? Because we know that the ball is accelerating fast down towards the Earth, but we don't experience the Earth kind of falling up towards the ball. Well, with a little bit of a look at that, we can see why. Because we know that acceleration is the force divided by the mass, F over m, from Newton's second law, F equals ma. So we can see that if we look at the acceleration of the ball, well, m, the mass of the ball, is very small. So the acceleration would be quite big. On the other hand, if we look at the acceleration of the Earth, well, it's the same force, if it is the same size, which is what I'm saying it is, then the same force divided by the mass of the Earth would be the acceleration of the Earth upwards. But we know that the mass of the Earth is huge, astronomically big compared to the mass of the ball, so the acceleration will be tiny, negligible, basically effectively zero. And so the ball we'll see the ball fall rapidly to Earth, but we won't notice any acceleration of the Earth upwards towards the ball because it's so insignificant. And someone's probably dropping a ball on the other side of the world at the same. Anyway, that's a joke. There's all sorts of things going on all around, and they're all insignificant. So that's how it works. That's a Newton's third law pair. So let's go back to our kind of zoomed in diagram and redraw it. So here's the ground again. I'm going to redraw my ball, and so how would I draw it on this diagram? Well, I'd just draw the weight of the ball acting downwards, and I'd have to draw the equal and opposite force acting upwards from down, strictly technically from the centre of the Earth, but obviously I can't fit that on this diagram. So that would be the weight, and this is the gravitational pull of ball on Earth. We still need to think about the reaction force though, because that does exist. So now it's in contact with the Earth again, we do have a reaction force, and because they're not moving, it actually is equal in size to the weight. But what is its pair then? Because if it can't just be on its own according to Newton's third law, it must have an equal and opposite reaction. Well, the reaction, what we call the reaction force, is a contact force. So it's the push of the ground on the ball, and its opposite force is actually simply the push of the ball on the ground. So I can draw that pointing down there, and I'll call that the push of the ball on the ground. So those are also a Newton's third law pair. They're equal, they're opposite directions. They're the same type, they're both contact forces, and they're acting on different bodies. One's acting on the ball and one's acting on the ground. So we've got two Newton's third law pairs in play. And finally, it's worth just looking a little bit more closely at what is a contact force. What's the origin of a contact force? Well, let's zoom in again, zoom in much more closely, and look at the boundary between the ball and the earth. So if there's the edge of the ball and there's the edge of the ground, then of course at the edge of everything's made of atoms and molecules, and at the edge of every atom and molecule are of course electrons. So what we can realise is, well, really we've got electron clouds at the edge of every object, and those electron clouds are negative charges, so they're obviously repelling each other. So a contact force is actually due to the electrostatic repulsion. So a contact force has an electromagnetic origin, and I'm just going to write electrostatic repulsion. So really, as the bodies get close together, the repulsion of the electrons just becomes so great that they stop their approach. So they're not technically touching. Oh, that's what contact is. It's electron repulsion. So it's just the electrons coming into contact, or the fields coming into contact. So worth another thing to think about. Well, I hope that clears up any misunderstanding about Newton's third law.